Thank you very much for the introduction and for the invitation. So yeah, like Johannes said, I'm going to be talking today about some joint work of mine with Bruno Chiarellotto from Padua and Christian Liedtke from Munich on good reduction of K3 surfaces. So just to kind of begin, I'm just going to set up some notation that's I'm going to use for the whole talk. So OK is going to be a complete discrete valuation ring. Still getting used to my graphics tablet. Big K is going to be its fraction field. Little k is going to be its residue field that I'm going to assume is perfect. But I'm not going to make any assumptions about characteristics. So OK could be mixed characteristic, it could be equicharacteristic, and the residue field could be characteristic 0 or characteristic P. These all work. But when it comes up, an auxiliary prime that I'm going to be using is always going to be assumed different from the characteristic of the residue field. Essentially, all the results do have an analog for primes equal to the residue characteristic, and if I've got time, I'll hopefully say a few words at the end about how to make the necessary changes. Okay, so I'm going to fix a separable closure of the fraction field. I'm going to let K bar, so this is going to be capital KS, little k bar is going to be the residue field of this separable closure. So this then is going to be an algebraic closure of little k, and then I've got my two absolute Galois groups of the fraction field and of the residue field. And then these are related by the usual exact sequence, where the Galois group of the fraction field maps surjectively to the Galois group of the residue field, and the kernel is the inertia group IK here. Can everyone see if I kind of circle this with my mouse? Is everyone seeing that?
Can you just do it again? I'm not sure I can see that.
So if I try and gesture with my mouse like this, by circling the inertia group, is that showing up on people's screens?
It's not showing up for me.
Oh, okay.
Yeah, for me neither, I'm sorry.
Okay, right. I'll try to bear that in mind. Okay, so the kind of general question that we're interested in is, if I take some smooth and proper variety over the fraction field K, how can I tell whether or not X has good reduction? So in other words, does there exist a smooth model of X over the ring of integers OK of this complete discrete valuation field, capital K? Okay, and there's sort of few classical results for kind of various nice types of varieties, in particular for abelian varieties and curves. So probably certainly the most famous and most well-known one of these is sort of the classical Néron-Ogg-Shafarevich criterion, which kind of in full generality was proved by Serre and Tate, and this is when my variety X is an abelian variety. What Serre and Tate proved, what the Néron-Ogg-Shafarevich criterion says, is that my abelian variety has good reduction if and only if the Galois action on it. So if I take my prime L, I can take its L-adic tape module in the usual way. This has a natural action of my Galois group, and then what the result says is that the abelian variety has good reduction if and only if this kind of Galois representation, this Galois action on the tape module, is unramified. So in other words, if the inertia group acts trivially. So just kind of another way of stating this, which is essentially just kind of sort of giving a different description of the tape module. This is if and only if the Galois action on the first etale cohomology group is unramified. Essentially because this is just this cohomology group is just the dual of the tape module tensor with QL. So there's also a similar but maybe not quite so well known result for curves. So maybe this is due to odor. What you might hope for curves is you might have again a very similar result where good reduction is detected by the first cohomology. This turns out not to be quite true, but you can fix it by instead looking at the fundamental group of C. So I can take the etale fundamental group, the geometric etale fundamental group of C at some base point. It doesn't matter. Take its pro-L completion. Sorry, it's pro-L quotient rather, I should say. And now this is going to have an outer action of the absolute Galois group because I don't know if I've necessarily got a base point that I can take defined over my field K itself. So without that, I can only in general get an outer action, but you have a similar sort of statement that C has good reduction if and only if this outer action of the Galois group on the etale fundamental group is unramified. So kind of these are the sort of classical results that we were basically looking at trying to extend to K3 surfaces. And at this point, maybe one kind of thing I'd like to emphasize is that in both these cases, if we actually have good reduction, so if we actually have some smooth model of either my abelian variety or my curve over the ring of integers, okay, then this smooth model is essentially unique. This is essentially due to the theory of Neron models. Neron models in the first case, and due to the theory of minimal models in the second case. And we'll kind of see in a little bit that this uniqueness is kind of this uniqueness is what fails for K3 surfaces, and kind of what makes is where the sort of interesting part of the question, or a large part of the interesting part of the question, lies. Okay. Like I said, I'm kind of interested in seeing whether you can say something similar for K3 surfaces. A K3 surface is just going to be a smooth projective geometrically connected surface over my field, capital K, such that its canonical divisor, which is defined as the top degree differential forms, is trivial. So it's just isomorphic to the structure sheaf, and such that the dimension of the first cohomology group of the structure sheaf is 0. So the first cohomology of the structure sheaf vanishes. And it follows from the definition of the K3 surface that it basically only has one interesting cohomology group. So this second condition here implies that the Picard scheme has to be etale, so its first cohomology group, its first etale cohomology group has to vanish. And so again, by Poincare duality and the fact that we're in dimension 2, we see that the only interesting cohomology group is H2. So H1 and H3, kind of H0 and H4 are fairly simple, or fairly simple to understand. So if we're kind of thinking about these results of Serre and Serre, Tate, and Oder, then the question we might be interested in is, can we detect good reduction by looking at the Galois action on the second cohomology group. And this is the question we were interested in. And maybe just a sort of helpful analogy, I just want to say a little bit about kind of what was known in the complex case, which was done. So this is sort of what was done in the analogous complex case by Viktor Kulikov in the 1970s. So in this setup, rather than taking our base to be a discrete valuation field, we take our base to be the punctured complex unit disk. So I'm going to let delta, as usual, be the unit disk in the complex plane. Delta star be the punctured unit disk, so the unit disk take away the origin. And I'm going to take pi a proper, or sorry, I should say a projective flat map of complex manifolds. So some flat family of complex manifolds whose non-zero fibers are all K3 surfaces. So such that at every point T non-zero, the fiber of this map at T is a K3 surface. So in this setup, the analog of the inertia action is the monodromy, right? So if I look at the fundamental group of delta star at some base point T, let's say, this is just a copy of Z, and this is going to act on the second singular cohomology group of fiber over my point T. And what Kulikov proved is that if this monodromy action here, this monodromy action here is trivial, then at least after making a finite flat base change on my of my disk, so just I pull back via some map of the form T goes to T to the N, then there exists a modification of my family such that actually this modification is a smooth family of K3 surfaces. So all fibers are smooth, and all fibers are K3 surfaces. The point here being the central fiber is the K3 surface. So modification here means a proper birational map, which is an isomorphism away from the central fiber. Okay, so somehow in more arithmetic language I started with, this is saying that if the monodromy action is trivial, then my family has potential good reduction. So it has good reduction after some finite base change. And just to quickly kind of sketch an outline of the proof, the first step of the proof, we use semi-stable reduction theorem. So what this says is that after making a base change like this, I can assume that the family is semi-stable. So in other words, the central fiber is a reduced strict normal crossings divisor in the total space. So once you've got a semi-stable family of K3 surfaces, what Kulikov then showed is that you could basically sort of modify a semi-stable family to produce a log K3 surface over the punctured disk, or rather over the disk with the 0 point considered as a divisor. So a log K3 surface is going to be kind of just a logarithmic analog of a smooth family of K3 surfaces. So a proper log smooth map such that so let me write this out actually. So kind of the key point here is that if I take the top degree logarithmic differential forms this time, then this is trivial. Okay, so we take our family, we make it semi-stable after a finite base change, we make a modification to make it logarithmic, and then the final step of the proof is essentially to classify possible shapes of the central fiber of log K3 surfaces. So users just write down what they have to look like, and in each case you can calculate the monodromy. And somehow what you see is that actually the only possible case in which the monodromy is trivial is the one in which actually the central fiber is smooth. So kind of very, very briefly, that's how the proof goes. Okay, so if we want to kind of try and do an arithmetic analog of this, then we run into one problem very, very quickly. And that is that semi-stable reduction is not known in either mixed characteristic or equicharacteristic P. And this is something that kind of we're not going to try to get around. We didn't really have anything to say about the general problem of semi-stable reduction. So what we actually are going to have to do is just assume that the K3 surface that we're interested in has potential semi-stable reduction. This is just going to be a blanket. This here is going to be a blanket hypothesis for the rest of the talk, essentially. But there are kind of some cases in which this is known. So, for example, it's known in equicharacteristic 0. So if the residue field is characteristic 0, then we know semi-stable reduction, potential semi-stable reduction. This might not seem particularly interesting, given that the complex case is already settled, or looks as though it's already. But actually, we'll see in a bit that our results do have something to say, even in equicharacteristic 0, if the residue field is not algebraically closed. So this is still an interesting case. It's also known if the residue field has characteristic P and X admits a polarization of sufficiently of of small degree relative to the characteristic. So if the characteristic is large relative to the degree of the case 3 surface, then potential semi-stable reduction is known, and this is due to Maulik. there are some interesting cases in which our results are unconditional. But anyway, so essentially assuming potential semi-stable reduction, Matsumoto in 2014 did give an arithmetic analog of Kulikov's argument. So it sort of transported the proof into the more arithmetic context. So what he showed is that if we take our K3 surface, again with potential semi-stable reduction, such that the Galois action on the only interesting cohomology group, H2, is unramified, then X has potential good reduction. So in other words, there exists some finite extension such that the base change of X to L has good reduction. So this is the kind of precise arithmetic analog of Kulikov's result that I explained just now. And actually, with just a little bit extra work, you can in fact assume that this finite extension is separable. So I mean, this is only interesting if you're working in equicharacteristic P, but you can do it. It's not too much extra work. But now it starts to get a bit more interesting when actually Liedtke and Matsumoto around the same time built on this and showed that you can actually take this finite extension to be unramified. So in other words, if the Galois action on H2 of a K3 surface is unramified, if the Galois action on H2 of a K3 surface is unramified, then this K3 surface acquires good reduction after a finite and unramified extension. And again, let me just quickly kind of give an outline of how you prove this. Well, if you know it has good reduction after a separable extension, you divide that into an unramified and a totally ramified extension. And what you just need to do is descend your smooth model over the totally ramified part. So we can assume that LOK is totally ramified. And then what they did is take a smooth model for the base change of X. So take a smooth Y for the base change of X to L. And what they show is that if the Galois action on H2 is unramified, then the natural Galois action on the base change XL, so the Galois group of L over K, sorry, I should say, I can assume it's totally ramified in Galois. So yeah, what they show is that the Galois action on the base change of X to L extends to an action on the whole model Y, and then if you take the quotient by this action, what you get is a smooth model. For X over OK this time. So this thing here is going to be a smooth model for X over OK. Roughly speaking, that's how the proof goes. And this is kind of this is sort of interesting, especially if we compare it to what we already knew for curves and abelian varieties. And a kind of very obvious question to ask is this unramified extension really necessary? For curves and abelian varieties, if you have good reduction over an unramified extension, then you already have good reduction without taking any extension at all. And so kind of a very obvious question is, can we really make this extension? Do we need to take an extension at all? And the answer turns out to be yes. And in fact, in the same paper, Liedtke and Matsumoto showed, or gave an example rather, of K3 surfaces defined over QP, at least for P at least 5, which don't have good reduction over QP, but which do have good reduction over QP squared, so over the applied extension of QP. So there are cases where you really do need to take a non-trivial unramified extension to get good reduction. And this kind of looks a bit disappointing because it basically says that there's no hope for getting any statement of the form X has good reduction if and only if sort of such and such an invariant. So if and only if some invariant has unramified GK action. There's just no hope that any statement like this is true, because if you take this example here, any invariant of it you write down is going to have an unramified Galois action. Ooh, was that a question popping up? Sorry.
That was someone who wanted to join.
Ah, okay, sorry. Okay. So I mean, this looks quite disappointing, and it looks quite strange if you're used to the results for curves and Abelian varieties. And I think somehow what's really is that for curves and Abelian varieties, smooth models, like I said at the start, are unique if they exist. And the fact that they're unique means that you're going to be able to descend them under unramified extensions like this. And somehow the problem is that when you pass to K3 surfaces, smooth models are no longer unique. So for curves, if we kind of think about what's going on in terms of dimension, smooth models for curves are arithmetic surfaces, right? And we know there's a good theory of minimal models and sort of uniqueness of minimal models for smooth surfaces. But now if we're looking at models of K3 surfaces, these are now arithmetic threefolds. And again, kind of if we think about the complex picture, we kind of know that the theory of minimal models for arithmetic for threefolds doesn't quite behave so nicely as that for surfaces. So in particular, smooth minimal models for threefolds are no longer unique. And it's somehow this non-uniqueness that's causing this sort of phenomenon to exist. And kind of what we'll see is that sort of to try to recover of this, something at least similar to, we're going to need to basically sort of look at exactly how that to what extent these models fail to be unique. I'm getting ahead of myself slightly. So what we then trying to do? I mean, essentially what we're trying to do is find some way to still explain this sort of phenomenon cohomologically. So even if we have a result saying that a K3 surface has good reduction if and only if this invariant is unramified, there's still something we could try to detect good reduction by looking at cohomology. So for now, for the rest of the talk, I'm going to take a K3 surface over my discrete valuation field K. I'm going to take some finite unramified extension of K, over which X has good reduction. So I can take a smooth model for the base change of X to L. And I'm going to let little kl be the residue field of capital L, and G be the Galois group of L over K, which is also the same as the Galois group of residue fields. I should probably also put Galois in here. Okay, so essentially the setup we've got is we've got a K3 surface that has good reduction over an unramified extension, and we want to tell when it actually has good reduction over K itself. How are we going to do this? Well, just as in the Liedtke-Matsumoto proof, we're going to look at the Galois action on the base change XL. So this just acts via its action on L, and this gives a rational action of G on this model curly Y. So this is going to be a rational action. It's an action via rational maps. And a key fact, which is a consequence of the Matsusaka-Mumford theorem, is that this action is defined away from finitely many inside the special fiber of this model curly Y. So a priori, it's defined just on the generic fiber, but I can actually extend it away from just a finite collection of curves on the special fiber. So in particular, I can actually restrict it. I can restrict the action to a rational action, the special fiber. So I get a rational action of G on the special fiber. Somehow, because the thing I started with is a K3 surface, you can actually show that this special fiber is now going to be a K3 surface. And so if you have a rational action, this then has to be regular. So after I've restricted it to the special fiber, I really do get a honest regular action. And if I have an honest regular action, I can take the quotient. And then this thing here is going to be a K3 surface over the residue field little k. And if I really did have good reduction over K itself, if I had a smooth model over OK, then this K3 surface here, this Roman Y here, is just going to be the special fiber of my smooth model, and moreover, by the smooth and proper base change theorem, I have an isomorphism between the cohomology of K3 surface I started with and its reduction. And this is going to be GK equivariant. So somehow, kind of in general, what's going on is that I can produce something that looks like it should be the special fiber of a smooth model, except I don't necessarily know whether that smooth model exists over OK itself. I might have to pass to this finite extension to actually get it. But if I do have a smooth model over OK, then the cohomology of X and the cohomology of this Y here are going to be isomorphic as Galois representations. And our main result is that the cohomology of this is true. So I can always produce this Y, and if the cohomology of this K3 surface Y here is isomorphic to the cohomology of the original K3 surface I started with X as Galois representations, then in fact X has good reduction over K itself. So without having to make this finite extension. So we don't have a kind of simple criterion in the sort of same way as the Néron-Ogg-Shafarevich criterion worked for abelian varieties, but there is still at least some sense in which we can detect good reduction by looking at cohomology. Now, kind of the reason for the failure of the naive Néron-Ogg-Shafarevich criterion is this failure of uniqueness of models. And somehow the way we're going to prove this theorem is by examining how this non-uniqueness affects or like manifests itself in the Galois action on the second cohomology. Because again, just like in the case of complex threefolds, the failure of uniqueness of smooth models of K3 surfaces is controlled by circle flops. And so what we're going to need to do is basically look how these flops are at this cohomology group here. But before I actually dive into the proof, maybe this is a good idea to see if anyone's got any questions about the statement, at least. Okay, if not, then I'll carry on. So the way these flops work is that again, I take my smooth model for X over L. And I take a -2 curve inside its special fiber. So this is some curve that's just isomorphic to P1 and that has self-intersection. And what I can do is I can form another smooth model for X, L, Y over here as follows. I first blow down this -2 curve C. This gives me something that's going to have a quadratic singularity. Let's say P at the image of this blow down curve C because this the two here. I'm then going to complete at this singular point. So this is going to look like some formal neighborhood of some quadratic singularity. This is going to have an essentially unique involution T that induces minus the, and then I can kind of reverse the process. So I can then algebraize and blow back up again. And what I end up with is a birational map to another smooth model for XL, which, which is, so F is an isomorphism. So I'm going to end up with this Y plus, which is going to be another smooth model for XL. It's going to contain -2 curve C plus, and this map is going to be an isomorphism once I remove these two -2 curves, but it's not going to be an isomorphism. It's going to be a genuine honest birational map. It's not going to be regular. So I mean, on a very kind of basic level, sort of what you're doing is kind of taking out the curve C and kind of gluing it in with some sort of opposite orientation in some sense. And kind of now what you can do is you can somehow look at how this flop here, this flop F, acts on cohomology. So so the point is the fact that it's an isomorphism away from just a single curve on the special fiber of each of Y and Y plus means that you can restrict it to the spatial fiber and get a well-defined rational map. And again, because these special fibers are going to be K surfaces, once you restrict that map here, cohomology, which is given by just restricting F to the special fiber. You also have an honest pullback map here on cohomology given by restricting F to the generic fiber. And then you have the maps coming from the smooth base change theorem relating the cohomology to the special and the generic fibers. And so you kind of write down this square that you think obviously has to commute, except it doesn't. So this diagram does not commute. And in fact, you can explicitly say how it fails to commute. You can say what the map is by starting in this this corner and following the diagram all the way around. So the failure to commute is the map which is given by reflection in the class of this flopped curve C here. So this is the second cohomology of the surface, so it has an actual intersection pairing on it. And so if we have some here, we can refine the map here. The composite map all around this square is reflection in the cohomology class of C. So somehow we can kind of detect the fact that this flop is not regular by looking at how it acts on coh. And this is somehow kind of the key point in proving the theorem. So the way we're going to take advantage of this is we're going to take a polarization on our original K3 surface X, which specializes to something which is big and nef on the special fiber of this model, curly y. This can always be done. So if I have my x and if I have my curly y and if I have my L, I can always modify curly y in such a way that this is true. So this is not a big assumption. And then what I do is I look at the collection of all possible -2 curves inside the geometric special fiber, which are orthogonal to this polarization. And we're going to assume that all elements of S, so all of these -2 curves are orthogonal to my polarization, are defined over KL. Again, I can always ensure this by increasing L if I need to. And then what we do is we define the Weyl group, which is really the Weyl group of X together with this polarization L, to consist of the subgroup of automorphisms of cohomology of the special fiber generated by reflections in all of these classes C. So for each -2 curve in this set S, I have a reflection. This gives me an automorphism of H2, and I just look at the subgroup of automorphisms generated by all these reflections. And now I can kind of if I look at the rational G action that I have in my model curly y, I can play exactly the same game as we did before for these flops. So now the point is that I can write down the map expressing the Galois action on y like this F sigma like this. Again, from what we saw before, this is something that it's meaningful to restrict to the generic and the special fibers on which it's going to be an isomorphism. And so I can write down exactly the same square that I wrote down before, and again, as before, this diagram is not going to commute in general. And so, given an element sigma of my Galois group, I get an element I get an automorphism of the cohomology of y just by following this diagram round in a circle, exactly as I did before. So I get an element, S sigma, which basically measures the failure of the square to commute. And now the key point is that because the failure of uniqueness of models of K3 surfaces is actually controlled by flops, this map here, this F sigma here, can actually be written as a composition of flops in these curves here. The upshot of that is that my element S sigma is really an element of the Weil group. So it's in from the Galois group to the Weil group. And what you can then show is that this kind of mapping has the constant value 1, so that S sigma is identically 1, if and only if the G action is regular. So this kind of intuitively makes sense because somehow S sigma was defined by measuring kind of the failure of, or sort of defined using the fact that the Galois action might not be regular, but you do need to do a little bit of work to get this. But anyway, what you can show is that S sigma is identically 1 if and only if the G action is regular. And so the point is that the G action is regular if and only if the model itself descends to OK. So the next key thing about this map sigma goes to X sigma is that it's a one cocycle. The point here is that the fact that all of these elements of S are defined over KL means that my Galois group G is going to act on them, and so if it acts on all the C, it's going to act on the Weil group. And what I get out is a non-abelian one cocycle for this non-abelian G module here, that is the Weil group. This is not a hard calculation. The other thing that you can show is that if you take a different model, then the two cocycles you get, so like I said, the two cocycles, let's say S sigma and S sigma primed, are cohomologous. And again, this essentially just follows from the fact that any two models differ by a composition of flops. Okay, so the upshot of all of this is that you get a well-defined element in a non-abelian cohomology set. And so you get an element in this non-abelian cohomology set that really only depends on X and the polarization L. And kind of given the four parts of the proposition, you can kind of probably guess what the punchline is now going to be, which is that X has good reduction if and only if this cohomology class is trivial, which is if and only if let me rephrase this. So X has good reduction over K if and only if there exists a model Y for which G action is regular, which happens if and only if this cocycle is trivial in this non-abelian cohomology set. So we do have some kind of way of detecting good reduction on the nose, We need to see whether this cohomology class is trivial or not. And now we can relate this back to cohomology, because the Wahl group was given to us as a subgroup of orbital morphisms of H2, and essentially, so just by functoriality, our non-abelian cohomology class S gives rise to a non-abelian cohomology class, this time with values in the group of automorphisms of H2. And again, if you kind of go back to how we constructed this, this cohomology class here essentially measures the difference between the Galois actions on H2 of the generic fiber and H2 of the special fiber, right? It was just defined by kind of the failure of commutativity of the diagram that you got by comparing the two actions. So essentially, just by construction, there's an there's a GK equivariant isomorphism between the cohomology of X and the cohomology of Y, if and only if this cocycle, this sort of L-adic realization of it, this cocycle this cohomology class SL is trivial. So now to kind of prove the main theorem, what we need to show is that the map we have in non-abelian cohomology has trivial kernel. So what I should say here, it's maybe worth mentioning that because these are non-abelian cohomology sets, because both the Wahl group and this general linear group here are non-abelian Galois modules, these cohomology sets really are just pointed sets. They're not necessarily groups. And what we really need is that this map has trivial kernel. In other words, that the pre-image of the distinguished point here is the distinguished point here. We don't necessarily need to know if it's injective. Interestingly enough, it actually works. But anyway, so I mean, the kind of basic idea of the proof is that we're going to replace the full H2 of Y by, let's say, the QL span of all of these -2 classes. And so this gives us a quadratic space V with the quadratic form given by the intersection pairing or the cut product that's actually going to be classified by a Dinkin diagram. Essentially the point is that the -2 curves that you're going to get in C are going to form some kind of ADE configuration. It's going to be classified by some Dinkin diagram, and then what you can actually do is basically just do an explicit calculation in each case. What the possible Dinkin diagrams can be. There's a fairly simple classification of all the possible Galois actions that you can get in each case, and you can just work out what these sets are and what the map between them is. And just very quickly, in the minute I have left, I want to say that we can have there is a p-adic version of this result. So if I want to choose L, my prime L equal to the residue characteristic, then, well, if I'm in mixed characteristic 0p, what I need to do is I need to change the hypothesis that H2 is unramified to the hypothesis that H2 is crystalline, and I need to change the G, and I need to change the condition that there's a GK equivariant isomorphism to the condition that if I apply Fontaine's function D cris to H2 of the generic fiber, I get the crystalline cohomology of the special fiber. And you can also recover statements in characteristic P, and I don't want to try and actually give a precise statement, but if you know about things, these are phrased in terms of fine modules over the rubber ring. Right, I think that's my time up. So thank you.